Hi, group of three people. I'm Satsa Soisa. My registration number is 4321, and we have Sajani holding the registration number 4318, and also we have Sandali holding the registration number 4329. So we for this big data project, we have selected an architecture, and also we have selected the project as the fraud detection system. Now, before the live streaming, I'll show you. I'll start with the architecture, so the full pipeline is very clear. So this project is a real-time fraud detection system, as I have told you, and it's built using a streaming data architecture. As you can see in there, at the core, we simulate financial transactions using a producer service. And then at the core, actually, as I told you, we are using a producer service. And so these transactions represent real-world events like payments, purchases, and transfers. So these events are sent into Kafka, which acts as a distributed message broker. Kafka is important because it allows us to handle high-volume streaming data reliably without losing any events. Next, we have Spark streaming, which consumes actually the data from Kafka in real time. Spark processes the incoming transactions, transforms them into structured format, and applies fraud detection logic. So after processing, any suspicious transactions are flagged and stored in PostgreSQL for further analysis. Finally, Airflow sits on top of the system and orchestrates the entire pipeline by scheduling it every 6 hours. So overall, this is a full end-to-end driven pipeline from starting from generate to store. So our pipeline is generate, and then we are streaming, and then processing, detecting, and storing. So this is how we have designed our architecture. And after that, I'll go to the orchestration layer. So as you can see, I have opened this orchestration layer from the port 8080. And then as you can see here, this is the Apache Airflow, which is responsible for scheduling and managing the pipeline. The DAC you see here runs every 6 hours automatically. That means I don't manually trigger any jobs. So everything is fully automated. And so if you look at the recent runs, you can see there are some of them are successful and failed, which confirms the pipeline is very much stable and running as expected. And so here, Airflow ensures that each step of the pipeline executes in the correct order and proves monitoring in case anything fails. So then let's go here. Now data is consumed by Spark streaming. And also now I'll move it to the live data generation. So we have producer, consumer, users, and also the Spark master running different terminals. So this is the live data generation. So this is JSON transaction. JSON transaction you can see here in the terminal. So you can see fields like user ID, amount, event time, merchant category, country, city, so something like that, and also the timestamp. So this simulates real-world banking payment systems where every transaction becomes an event. So these are the so these events are immediately pushed into Kafka. So Kafka acts as a buffer that stores streaming data reliably. So one key advantage of Kafka is that it decouples data producers and consumers, meaning the system remains stable even if downstream processing is temporarily slow. And so when we are going to this Spark master stream processing, so this is Spark jobs. So this data is consumed by Spark streaming. Actually, the Spark processes the incoming data in micro batches, which allows to handle high throughput streams efficiently. So in this step, actually, the raw JSON data is transformed into structured format and prepared for analysis. So we can see the logs from here, and you can see there are a lot of logs also. Yeah. So in this step, actually, so this is also where the data cleaning happens, and also this is about the registration, the manager. So we have transport plan factory managers. So everything is be done here. I mean, as I said, this is where data cleaning happens, such as passing timestamps and ensuring consistency in the dataset. So most importantly, this layer enables the real-time processing, meaning fraud detection happens as transactions arrive, not after storage. And then let's look at, so as I told you, this will be stored in the so now, so this is the actually now we move to the output layer, the fraud detection results. So instead of storing every transaction, we only store the suspicious one, and also we only store suspicious and anomalous ones. So this system detects multiple types of fraud patterns. So for an example, we have impossible fraud type actually. You can see here impossible travel. So impossible travel this explains where a user appears in two distant locations within a short. And also we have one high spend one. That means high value transactions that are significantly higher than normal spending behavior. And we have unusual patterns based on high user stories and geography. So each record contains the user ID. So these are the user ID and also the event timeline, merchant category, amount, country, city, fraud type, and the detection timestamp. Everything is recorded here. This makes actually it easy for downstream systems to analyze fraud trends or trigger alerts. So in a real banking system, actually these alerts could trigger automatic account verification or fraud investigation. So this is our architecture, and also let's if you look at the architecture again, So to summarize, this project actually demonstrates a complete real-time fraud detection pipeline. We start with data generation, stream it to Kafka, process it using Spark, detect fraud in real time, and store results in PostgreSQL. So the entire system is orchestrated using Airflow to ensure reliability and automation. This architecture actually closely reflects real-world fintech systems used in production environments for monitoring. And if I'm going here, so we have Spark Master. So as you can see here, it has the metadata of the Spark Master, the live workers, codes, and everything, whether the status is live or not, and Spark Worker. And you can see here also the metadata of the Spark Worker. And we are using two cores, and also memory, we have 2 GB, and the job details also. So this is our project, and this is our architecture. So thank you very much.